Hello everyone, our final year project is Spatial Audio Navigation for the Blind. We know that with the development of technology, more and more 3D depth sensing cameras have come out to the market, and in recent years, people have successfully embedded 3D cameras into VR devices. By analyzing the depth information provided by the camera, VR headsets can build a corresponding virtual model and then perform positional tracking. Inspired by the VR headsets with 3D cameras, we were wondering if we encode the depth information not into video but into audio, will people still have the ability to interpret it and then reconstruct a virtual environment in their minds? If that is possible, then with 3D cameras, we can develop a new powerful navigation device for the blind. So the objective of this project is to prove the feasibility of this idea. And we aim to provide an exploratory system design and to find out the real-world difficulties of this problem. Last semester, by making use of sound characteristics like quality, pitch, and loudness, we have implemented an alpha version of our testing model. We split the image into 3 columns from left to right horizontally, and the 3 sounds are generated one after another in a cycle. And vertically, the mean value of the depth data at the same height will be proportionally mapped into the pitch and loudness of the audio information. So for each sound, its pitch and loudness are changing during the sustained period of time. At first, we thought this method can tell users the vertical depth distribution of the image. However, after testing, we found that it is not easy to get information from those continuously varying sounds in a short time. And those sounds are not very pleasant to listen as well. So this semester we made some improvements.
So in this semester, we made 4 major improvements and optimizations. Firstly, we increased the resolution into 3 by 3 blocks. So you may see 9 blocks for each sample frame. And for each block, we will have a depth information to represent the entire block. There is a single sound mapping with the depth representations. The sound has a certain pitch and loudness so that we can squeeze each period of the sound and increase the frequency of the entire cycle. In this way, people can work faster than using our alpha version. The second improvement is about sampling strategy. In our alpha version, we sample the image from video stream frame by frame. For each frame, there will be 3 sounds to represent the situations. However, during our tests, we found the users are turning around their heads frequently, and the sound effect is always behind what they are looking at. So instead of sampling entire frame, we sample a column from the image. For each column, we sample the current frame from the video and crop the column out, and generated 3 sounds from bottom to top. Consequently, the user will hear the sound that is always mapping with the real-time situation. Thirdly, we optimize our block representation. Originally, we used median distance to represent the situation. We found that it is relatively vague in reflecting the authentic environment. Now, we use median distance instead, and found it is a better representation for each block. To reduce the computational burden, we sample 1 pixel out of 9 pixels around, and calculate the median distance of the sampling pixels. This distance will be further mapped into a certain sound effect. Lastly, we quantize the sound pitch into 15 levels. Using a fixed pitch, the user-friendly of the sound effect is increased by a large step. For the closer block, it will have a wider representation in the depth image, and correspondingly a higher pitch sound effect. people can identify the situation by distinguishing the generated sound pattern, and the performance is dramatically increased in our beta version system.
After the implementation of our new solution, experiments are done to evaluate the behaviors and the performances. The experiments include 3 parts, including the unit test, speed test, and the system test. For the unit test, the overall evaluation is listed in the table. As you can see that there are totally 6 testing scenarios. For example, the wall, the corridor, and for each scenario, it is evaluated into 2 fields, identification and navigation. The field identification means whether it is easy for the blind to identify that which scenario he is locating in, and the field navigation evaluates that after the identification, whether the information is enough to navigate in that particular scenario. For the scenario of wall, both the night blocks are bright because it's very close to you, so the spatial audio will be in both high pitch. Then the blind knows that there is a huge obstacle in front of him. He may identify that it is a wall and tries to turn left and right to find where he should go. For scenario of the corridor, the left and right column will be in high pitch because of the wall, and the sound in the middle column will be in low pitch because it is far away from you. This pattern helps the blind to identify the scenario of corridor, but the blind still needs to turn around his head to ensure that he is keeping in line and does not hit the wall. And if an obstacle is standing in front of you, let's say a person, compared with the scenario of the corridor, the difference is that the sound in middle column will also be in high pitch to alarm the user, and the blind need to stop or turn around to avoid the obstacle. As for the scenario of the stairs, the distance between the footsteps and the blind is increasing with the extending of the stairs, so the sound in column is also changing from the higher pitch to lower pitch. This sound pattern can help the blind to identify the stair, but the blind may not know how far is the first footstep of the stair is, so that the navigation becomes harder. Moreover, the sound pattern of stairs is the same as the slope. Both of them have an increasing distance from the blind, which may be ambiguous to identify. And to evaluate the full performance and the real-world surroundings, a tester tries to navigate himself using the system with his eyes closed. Generally, for the speed test, the maximum working speed is 1.6 to 5 meters per second, which is quite acceptable. We believe that the speed can increase with longer training time for tester, and during the system test, the tester can successfully navigate himself and avoid obstacles. But under more complicated surroundings, the performance is not good enough due to the limited information, which need to improve in the future. After the experiments, we have found some limitations of our system and try to solve it in the future work. Firstly, we are considering a smarter sampling method because we are now calculating the median distance of a block, and each pixel is equivalent. The smarter way is that some pixels which are closer to you takes higher weight, and the further pixels takes lower weight. This will help to improve the accuracy as well as the security of our system. Secondly, the system now does not perform well in this complicated surroundings due to the limited 3x3 blocks information. So in the future, we will add extra blocks to provide more information by finding the minimum resolution for navigation. Lastly, we are expecting a lazy learning mode that only learns the user when something different or something emergent happens. We should utilize the video processing technique. This is all we have done in this semester. As a conclusion, after finding the weakness and limitation of our alpha version, we make some improvements in sampling strategy, increase resolution, block representation method, and quantize the sound pitch. As long as enough information is provided through the spatial audio, the blind can reconstruct the visual image. And for the more complicated environments, we will focus on compromising the navigation accuracy with the sound information. After this, we believe that finally the blind can navigate like normal people one day in the future.